Swayam Prabha. Digital India. Educated India.
What we will discuss is that so far the linear momentum balance was viewed from a control volume point of view. What does that mean? You derive the balance equation taking a small control volume, then we shrink it to a point, and then we were discussing in terms of rate of change of momentum, of course all per unit volume, rate of change of momentum in that small volume, and whatever is whatever momentum flowing in, flowing out, and then right hand side we have sum of all the forces. Okay. Now we are going to take a different look at the left hand side. Right hand side is going to still remain same, and that is why the title says linear momentum balance from a material particle viewpoint. Okay. Let us go through that and then you will understand the title clearly. Okay. One other importance of this slide is that we are going to do this series of steps later on also few other places in the course. So, we will repeat this later on as well. So, the idea of this discussion is that we have derived the linear momentum balance and interpreted the left hand side in terms of what is happening over a small region, rate of change of momentum in that region and whatever momentum flow entering and leaving in that region. We are going to have a different viewpoint for the left hand side. Let us see how do we do that. Maths is simple. What I do is just use product rule and expand the derivatives on the left hand side. Okay. Now the first term, it is dou by dou t of rho Vx. So, rho into dou Vx by dou t and then Vx into dou rho by dou t. Now come to the second term, there are three terms there, rho, Vx and Vx. Based on the significance what we have seen earlier, we will combine rho Vx together and this Vx separately. Similarly, rho Vy separately and Vx separately. Similarly, we will combine rho Vz and Vx. Okay. Why is that? We know the significance of rho Vx. Vx is the volumetric flux, rho Vx is the mass flux in the x direction, y direction, z direction. So, when I apply product rule for this differentiation, I keep rho Vx separately and then write dou Vx by dou x and then Vx into dou Vx, dou of rho Vx by dou x. Similarly, in the y direction, similarly in the z direction. What is that we have done? Taken the left hand side, applied product rule for all the terms. First term is very straightforward. For second, third and fourth term, we have clubbed rho Vx together and Vx separately. Okay. Why do we do that? Significance of rho Vx is the mass flux, and you will see why do we do that next step as well. And you see some colors in the equations, we will understand what they mean as we go along. Okay. So, what we do, I combine all the terms which are highlighted in blue in terms of blue color. So, the first term is rho into, rho is common to all the blue colored terms. So, let us take out rho, then you have dou Vx by dou t, then if you take this term we have Vx into dou Vx by dou x, then if you take this term we have Vy into dou Vx by dou y and similarly Vz into dou Vx by dou z. So, combine all the blue color terms. Let us combine all the red color terms. Now Vx is common, if you look at all the red color terms, Vx is common. Now let us take Vx out, then you have dou rho by dou t from this term, then dou rho Vx by dou x from this term, then similarly you have dou rho Vy by dou y and similarly dou rho Vz by dou z. So, combine all the blue color terms and the red color terms. Now terms in the bracket of red color term is the equation of continuity, we know that goes to 0 both for compressible flow and incompressible flow. Okay, no assumptions here. So, second term just vanishes, the terms inside the square bracket is nothing but the continuity equation or the differential mass balance is equal to 0. Okay. Okay. Now left hand side, if you look at that, of course we discussed the substantial derivative many classes earlier, and we also mentioned that we will come across later in the course. This is the point where we are coming across the substantial derivative. If you look at the terms in the within the blue square brackets, they are nothing but dou by dou t, and these three terms represent v dot del operating on Vx, dou by dou t plus v dot del operating on Vx, and of course this we know is our substantial derivative operator. So, the left hand side can be written as rho capital dVx by dt. Rho is the density and dVx by dt is the substantial derivative of velocity, of course in the x direction. So, what is that we have done? We have taken the left hand side and did some simple mathematical steps, use the equation of continuity, and then we have proved that the left hand side can be written as rho into dVx by dt. As I told you, we will come across similar steps later on, energy balance also and later as well. Now, let us rewrite the linear momentum balance expressing the left hand side in terms of this substantial derivative. So, left hand side becomes, of course, I would say easier to remember also compared to the earlier linear momentum balance. This equation is easier to remember and starting point for many problems as well. So, many applications start with this form of the linear momentum balance equation and easy to remember. So, left hand side now says rho dVx by dt is equal to, of course, right hand side there is no change, I do not want to repeat it, okay. It is the same as what I had seen earlier. Now, how does the significance change, how do we interpret this equation? The left hand side, if you read it, first you have density which is mass per unit volume, and then that is multiplied by dVx by dt, of course we know is acceleration of a material particle. Remember what was the significance of substantial derivative? The derivative following a fluid particle. So, dVx by dt represents acceleration of a material particle, of course material fluid particle. What is there on the right hand side? Forces acting on the fluid particle. What is this? Nothing but Newton's second law, but for a continuum particle, continuum fluid particle, of course. So, the left hand side interpretation first when we wrote the first time was, we have a small volume, there is some rate of change of momentum entering and leaving, etc. Now, the left hand side interpretation is different. You are following a fluid particle and it represents mass into acceleration of that fluid particle, of course divided by volume, density into acceleration of that fluid particle. The left hand side has changed from an Eulerian viewpoint to a Lagrangian viewpoint. Earlier it was for a fixed volume, what is happening in the small region. Now, if you follow a fluid particle, how does its density into acceleration change, and that is nothing but governed by the forces acting on that fluid particle. Now, if you remember, all this started from our Newton's second law of motion. For a system, what happens when you make the size of a system go to 0? You get a fluid particle. Why? We said a system is made up of several fluid particles. So, if you take a system of finite size and shrink it, you get a fluid particle. That is what we had got now, because remember in the derivation we shrank to a particular point. So, we started with Newton's second law of motion for a system. The different, now this equation is also is for a fluid particle. How do you relate? When you shrink the size of a system, it becomes a fluid particle as it goes to 0 size, and that is why the left hand side now represents the density into acceleration of a fluid particle. And one more observation is that the left hand side are all called as the inertial terms. What is inertial terms? The left hand side are all the inertial terms. Okay. Now, independent of how do you view the inertial terms, how did we view the inertial terms in the first instance? It is based on a fixed control volume. Second time we interpreted the inertial terms in terms of a moving fluid particle or a material particle. Independent of that, the right hand side is same. There was no change in the right hand side. So, whether you view the inertial terms in terms of fixed control volume, as if there is as in terms of change of momentum, momentum entering and leaving. Either you take that viewpoint or you take the viewpoint of a moving fluid particle. What is that? Density into its acceleration. The right hand side is independent of that, independent of these two viewpoints. Okay. Now you look at the title, linear momentum balance from a material particle viewpoint. So two different ways of writing the linear momentum balance equation. We have discussed at length the first viewpoint. Okay. Second viewpoint just requires a rearrangement of the left hand side, including the continuity equation, and you get this viewpoint. See how just rearrangement gives a different, completely different viewpoint for the left hand side. Of course, right hand side is sum of forces acting. Okay. We will proceed to the next topic. We said closure problem. To understand closure problem, we should understand the terminology degree of freedom analysis. It is a very common terminology which we come across frequently in mass energy balance calculation in a process calculation course. Okay. Just as a quick revision, we will have a simple example to explain what degree of freedom analysis means. Okay. First of all, what is use of degree of freedom analysis? It helps to determine whether a system of equations can be solved or not. Okay. In terms of a mass energy balance calculation, suppose if you are given a problem, if you do a degree of freedom analysis, you can find out whether enough information is given to you, so that you can solve for the rest of the unknown variables. Usually your flow sheet will have some known variables, unknown variables. You do a degree of freedom analysis and find out whether enough information is available to you, so that you can solve for rest of the unknown variables. Okay. In fact, the Gibbs phase rule, which all of us are familiar with, is f is equal to c minus p plus 2, number of components, number of phases. That is also an application of degree of freedom analysis. Okay. Of course, that is in terms of intensive variables. Okay, how do you define degree of freedom? Degree of freedom is defined as number of variables minus number of equations, more formally number of unknown variables, number of independent equations. The equations which account for should be independent of each other, which means you should not be able to get one equation by a linear combination of other equations. Okay. For our purpose, all of the equations are independent. Okay. A number of variables are unknown variables. Let us take a simple example. Let us say I have a system of algebraic equations. Okay. X plus y equal to 0, x plus 2y equal to 3, and I want to find out whether this system of equations can be solved. So, I can do a degree of freedom analysis. The number of variables are 2 here, x and y. The number of variables are x and 2, namely x and y. We have two equations and giving 0 degrees of freedom. So, 0 degrees of freedom tells you that we can solve this set of equation. Now, let us take another example. This can be solved. Okay. Now, let us take another example, x plus y equal to 0, but now second equation is x plus 2y plus z is equal to 3. Now, if you do a degree of freedom analysis, there are 3 unknown variables x, y and z, x, y and then z. Only 2 equations are there, giving us 1 degree of freedom, which means that I cannot solve the system of equations unless you specify z. Okay. Now, if you specify z as a function of x, y, if you replace x with some function of, let us say x plus y or x into y, some equation, then what happens? You have 2 equations, 2 unknowns, then you can solve this system of equations. Okay. And we have illustrated here for the case of algebraic equations, need not be algebraic, it could be ordinate equations, partial differential equations. Okay. We are going to see an application for partial differential equations, because our conservation equations are partial differential equations. Okay. So, degree of freedom analysis tells you whether a system of equations can be solved or not, defined as number of variables minus number of equations. We have seen 2 examples where one degree of freedom is 0, the second one is degree of freedom is 1, but if you express z as a function of x, y, it can be solved, and that is the point you should note. We will carry over this. If you understand this, it becomes very easy to understand what we are going to discuss now next. Okay. Okay. the topic which I am going to discuss now is formally called closure problem. We will understand why is it so as we go along. Okay. So, let us write down all the equations which are derived so far, the total mass balance, of course the differential form, and then we will write the linear momentum balance. We have to write all the 3 components, the x component, the y component and the z component. And then remember this rho is the density. So, we need an equation of state, we will have to include that as well, which comes from a thermodynamic course. That equation of state could be an ideal gas equation or non ideal gas equation. For simplicity, for example, we take a ideal gas equation of state. Now, let us do a degree of freedom analysis for these set of equations. We have the total mass balance, the linear momentum balance and the equation of state. Just want to repeat, the equation of state is required because we have density, and we said that then the density is related to pressure and temperature, and that relationship should come from a equation of state. Okay. The equations are repeated here. We will do a degree of freedom analysis now for these set of partial differential equations. Rewriting the mass balance equation and the differential momentum balance equation, and of course the equation of state. So, now let us account for the number of variables, number of equations. When I say variables, I mean the dependent variables, not the independent variables like time, x, y, z coordinates. Okay. What are the number of independent variables? We have rho, one count, velocity is a vector, 3 components are there. So, it adds 3 more variables. We have pressure, 1 more variable, and then we have this 9 components of the viscous stress tensor. Okay. But we proved that the cross shear components are same, leaving us only with 6 independent viscous stress tensor components, and that is what is written here. So, totally we have 1 plus 3 plus 1 plus 6, 11 independent variables, density, 3 components of velocity, pressure, and only 6 components of viscous stress tensor, because the diagonal 3 diagonal elements, and of the 6 off diagonal only 3 contribute because they are equal to each other. Number of equations, you have 1 mass balance, 3 linear momentum balance, okay, and 1 equation of state, giving us 5 number of equations is 5. So, find the degree of freedom as 11 minus 5 is equal to 6. We have seen in the previous example that the degree of freedom should be 0 for the system of equations to be solved. We have now a huge number of 6, of course, which means that we cannot solve. Okay. And what are the 6 unknowns? They are very clear, because the 6 components of the 6 independent components of the viscous stress tensor are the unknowns. If you express that in terms of the usually existing variables, if you express that in terms of the already existing variables, just like we did in the last example, what did we do? Z in terms of x and y. Similarly here, if we express this tau, the components of tau, let us say tau xx, tau yx, etc., in terms of velocity, then this degree of freedom will become 0. Okay. Not exactly velocity, you will see later on that we are going to express in terms of velocity gradients. Okay. And we take a diversion to solid mechanics to understand what velocity gradients are. Understand velocity gradients, we will understand what displacement gradients are, and that is why we take a diversion too. So, as usual, any difficulty we run to solids. So, we will take a refuge in solids again. Okay. And let me explain that with this journey to the Navier-Stokes, and where are we now and where are we proceeding. Now, we are here to begin with. We started with Newton's second law of motion for system, applied the Reynolds transport theorem, derived the integral form of linear momentum balance, applied this for a small control volume, derived the differential form, the left hand side and the gravity on the right hand side. To understand surface forces, we went to solid mechanics, understood stress vector and stress tensor, applied that to fluids, discuss fluids under rest, to discuss hydrostatic stress, discuss about total stress tensor in terms of the hydrostatic stress and the viscous stress tensor for fluids. With all this, in the previous lecture we applied we completed the right hand side of the linear momentum balance, and now we are ready to understand this, the differential form of linear momentum balance. What does it include? Of course, the left hand side is there. On the right hand side we have gravity, we have pressure and viscous stress. When we are going to solve for pressure, the viscous stresses are unknown. We want to relate this viscous stress to velocity, actually velocity gradients. Understand velocity gradients, we should understand what displacement gradients are, and that is why we take a second diversion here, go to solid mechanics, understand displacement gradient, and then we can understand velocity gradients. Okay, and that is where we are. Looks like almost we are there, but we need to understand furthermore. Okay, and this problem is called the closure problem. That is, closure meaning that expressing the components of the viscous stress tensor in terms of velocity gradients. You close the system of equations. Okay, to summarize this part, we completed the differential linear momentum balance in the right hand side, including the surface force on the right hand side, and we included the surface force due to pressure and due to viscous stresses, and we also discussed the viscous stress tensor and the convective momentum flux tensor as well. Okay. Viscous stress tensor is kind of known to us because analogous to tau for solids. The convective momentum flux tensor is new to us. Okay. We also discussed the closure problem, which means that the components of viscous stress tensor are unknowns. They need to be expressed in terms of velocity, or more precisely velocity gradients, and to understand displacement gradients we take a diversion to solid mechanics.